to derive the mean formula for a binomial distribution, which is this thing here. That's simply the expectation value or average is the number of trials multiplied by the probability of success. One thing that's important to note about n and p is that they are constant because in the binomial probability distribution, you assume your events are independent of each other. This here is the PDF for the binomial distribution. I might go over basics, how you get this from the binomial theorem later on in a different video. But all we need to know is that it's independent and that the expectation value formula is x times p of x all summed up together. So how do we go and get this formula from an outline of steps that Probabilistic World in his blog post kindly shows us? Well, first off, we note the following. Note that at x equals 0, e of 0 equals 0, so we can ignore the 0th term, and so we start counting at the first term, x equals 1, and add up all the n minus 1 terms that are left there. After that, we rewrite the variable binomial coefficient in factorial form, which is this thing here. Now, because the binomial events are independent, we expect to get a constant answer that doesn't depend on the variable. So we're allowed to intentionally factor out a single factor of n and p in order to cheat. And for this factor here, which is the probability of failure of 1 minus p, the exponent n minus x, we're going to introduce an arbitrary zero pair of addition, plus 1 minus 1 to be precise. And you'll see later on how that is helpful, because after we arrange those terms by distribution of the negative sign and commutative addition, we will get a nice term that allows us to make two careful changes of variable for the lower upper indices of summation and the entire PDF expression, which is this thing here. We will refer to this later on. And the coup de grace, assuming our events are disjoint, that means the intersection between all the possible events in the Venn diagram this representation are empty. There is no overlap. The sum of probability over the entire sample space is 1. Now, let me go and try typing out the entire proof in one flow. So the expectation value equals this finite sum from 0 to n over here. But we plug in x equals 0 to here, we just end up getting like a single term of 0. Therefore, we can just write this as 0 plus the summation from x equals 1 all the way to x equals n. So we've already accounted for the 0th term at 0. We can ignore that and look at all the other remaining n minus 1 terms here. That becomes then x, c of n, choose x, p of x, 1 minus p to the n minus x. But now note that now we're going to expand this into factorial form. We know that c of n, choose x, equals n factorial over n minus x factorial times x factorial. So then this just breaks up to become just gotta be careful with this thing here. Okay, n factorial over n minus x factorial here. Okay, now we factor out an n and a p from here. And we can bring it outside the summation symbol because n and p are constant with respect to our dummy variable, which is x. So then this becomes np summation of x equals 1 to x equals n. That becomes x. The n factorial becomes an n minus 1 factorial over n minus x factorial, x factorial. We get p to the x. We factor a p out from there, so that leaves us with x minus 1 p's instead of x p's here. And that's times by 1 minus p to the n minus x. Now, using the recursive definition of a factorial, x over x factorial can be simplified. In fact, it becomes x over x times x minus 1 factorial, which then just becomes 1 over x minus 1 factorial. So then we can replace this with you can get rid of this x here and replace this with x minus 1 factorial there. Very nice. And now this can be written into a nice form. This is simply in compact notation, the same thing as np, some, x equals 1, x equals n, n minus 1, choose x minus 1. Yep, that's it. Then we have p to the x minus 1 times 1 minus p to the n minus x. And now here, as I said, we're going to introduce the arbitrary zero pair. Introduce the zero pair plus 1 minus 1 in the exponent for 1 minus p. Oh my god. It happened again. For 1 minus p, 1 minus p. Sorry, technical difficulty there. And then carry on from there. np, copy this. Have this here, then we get like plus 1 minus 1 over here, but we're going to go manipulate it in like a weird manner. Now we're going to go and like commute the ones or rearrange them. So I'm going to get n minus 1. Oops, sorry, didn't notice that there. Okay. I'm going to bring the I'm going to bring the negative 1 here, right next to the n here, and the 1 and the negative x are going to go with each other. Negative x plus 1. Now I'm going to do something very sneaky. This plus 1 is essentially going to become a double negative at this point. So this is minus 1. And then if you factor out negative 1 from there, well, that's just ends up giving you np. Oops, not large enough. N minus 1 minus x minus 1. Once you factor everything out from there, that's what you get. You can check it more carefully. And now we make our change of variables. So where did I put it here? We let n minus 1 equals m. And then another line, x minus 1 equals j. But here's the thing. We can set x to be whatever number we want because it is a dummy variable. So let x equals 1, 1 minus 1 equals 0 equals j. So the bottom index becomes j equals 0 over here. And if I let x equals let x equals n in the equation x minus 1 equals j, I get n minus 1 equals j. But by definition, we already let n minus 1 equals to m, so m equals j. So given this, I can rewrite this as np and change the indices now. This will become j equals 0 to j equals m. And then look, see here? We have a perfect copy of n minus 1, x minus 1, and n minus 1, and x minus 1 here. So this can simply be replaced with m and j. So it's m choose j, or c m choose j, like this. I need to stop mixing around the notation. Yes, I mixed around the notation. Oh dear God. Lord help me. Okay, whatever. At least you understand it, hopefully. And then this is times p to the x minus 1. Now this is times 1 minus... Oh, wait, sorry. X minus 1. We don't want x's anymore. X equals... What was x equal to? Ah, okay. Since this is x, and we have x minus 1 equals j, x minus 1 equals j, so x equals j plus 1. Okay. Let's see, p to the x minus 1. Oh yeah, that's just j. X minus 1 equals... Okay, yeah, there it is. X minus 1 equals j. Okay, so then there's p to the j. There's no need for that. Sorry. Okay, p to the j, and then we have 1 minus p. There we are. 1 minus p. N minus 1 is m. X minus 1 is j. There we go. We have n minus j there. Boom! Very nice. And then, finally, because the events are disjoint, this probability has to equal 1. Boom. And with our that, we are done. Now, proof essayist, probabilistic world uses a combinatorial identity to go and break up the steps, so you can prove it in different ways. That's the thing with combinatorics. There are so many different ways you can prove things, it sort of becomes like a headache after a while. So feel free to consult his, and I credit like his work, if you want to. Otherwise, I think I've done my job. And from next here on, I will go and derive how we get the variance of a binomial distribution, which involves using the second moment of probability. So stay tuned for that. Until then, I hope you enjoyed the video. Please let me know in the comment section if there's anything I can do to improve my teaching and exposition. Thank you and have a pleasant day.